I'm just going to crack on. I think there's some people that are kind of milling around and stuff. That's fine. Right, so I'm going to speak to you this morning about, they've had to kind of turn me down because I'm a bit more, active, I think. So I'm going to speak to you about designing wireless for Apple devices. I'm a wireless engineer. I do this all day, every day, and I don't just do it for Apple devices, but I felt like that was probably appropriate for here. Apple devices are really good with Wi-Fi. What I'm going to do is I'm going to give you some kind of like Wi-Fi 101 type stuff so that we've all got like a very kind of basic fundamentals of how Wi-Fi works. Because what I've realized in my time doing wireless is that a lot of kind of traditional routing and switching people don't necessarily know how that translates to Wi-Fi. So let's have a quick look. So like I say, I'm going to go through some kind of basic stuff. We'll talk about iOS and macOS specific roaming. We'll have a look at Apple Wireless Direct Link, and then some of the tools that I use and other things. Okay, so the first main thing that is pretty important when we're talking about wireless is that we use the dB scale, right? Now that's a logarithmic scale, not a linear scale. And so when I'm talking about 10 dB, 10 dB is not half the power of 20 dB. It's actually 10 times less power than 20 dB. And actually, it's every 3 dB, the signal doubles. Or every 3 dB taken away, the signal halves. And so you can see that on the kind of the chart I've given you here, right? So most APs, the APs in here, for instance, are set for an ERIP of 9. So they're giving out 9 decibels of energy. So you can see there that that's 8 milliwatts. So on a standard AP, you might say something like, we've got 14 as our maximum, and it would be 0.25 watts. Now, the reason why I bring this up is because I hear a lot, oh, you're not putting that AP in my office, are you? I get headaches from the AP, right? Well, if that AP is hitting your device at neg 67, that means that there is 0.000001995 of a watt of energy. So there's more radiation coming off of the light bulb than there is off the AP. Really important to know. Great, so Wi-Fi, at its kind of most basic, works like a walkie-talkie, right? So it's very much, there's a lot of overhead that has to happen. There's a lot of, over, right, yeah, I'm gonna talk now, da, da, da. And the way that kind of plays itself out, it's not like cellular. Cellular phones, there is a scheduler for cellular, right? So cellular will say, right, you're going to talk for 3 seconds, you're going to talk for 5 seconds, then you're going to talk for 8 seconds, and then and it schedules out what's going to happen. Then it says go, and everyone does what they do, and you get to hear from lots of devices all at the same time. That's not how Wi-Fi works. Wi-Fi works one device, including the AP, at a time. Now I can hear some people thinking, not with Wi-Fi 6, Dan. Yes, actually, still with Wi-Fi 6 at the moment. Hopefully that will change. So what I want to do is just quickly kind of explain to you how that works. Now, I'm part of a kind of Wi-Fi engineer community, and we have this way of explaining how the contention window works called the game. I'm a bit of a nerd. I like to play D&D, and so I've got my sets of dice and things like that. The way that wireless works is a lot like rolling a D20. And what we've got to try and do is get the lowest number possible so that we get to 0, then I can start sending my data. And that's all well and good if I'm the only person rolling a dice. And I can, I roll a 14, great, I just count down 13, 12, 11, 10. Once I get down to 0, I can send my data. The problem is, if I've got another 20 people all rolling a D20 dice, chances are there's going to be a few of us that roll the same number. And so then what we get over the air is a collision where we're both trying to talk at the same time. We both have to kind of go, oh, sorry, there's a bit of a Zoom kind of thing. Oh, no, sorry, you talk, whatever. Right, and you have to stop. And so what happens is that we then have to double the amount of time that we can roll, right? So instead of rolling a D20, I'm now rolling 2 D20s, and I have to add those numbers together, and then that's when I get to talk. And so hopefully the kind of thing that I'm trying to explain here is there's a lot of overhead with Wi-Fi. There's a lot of wasted time with overhead. And so one of the best and one of the worst things about Wi-Fi is it's super, super resilient. So you can have a space like this that's designed suboptimally, and it will still work, right? And that's one of the best things about Wi-Fi, but it's also one of the most infuriating things, because if they just did it properly, then it would work even better. And so this is what happens when the clients collide, and when you get a room like this where there's lots of people in the same room and all the devices are trying to send data, what you'll find is that we get down to kind of 4 or 5 retries. And so that kind of space where you get to send something, and then people go, oh, Wi-Fi's slow. Well, yeah, that's because there's a lot of retries. That's because there's a lot of collisions. So how can we combat this? Well, through design, but also we can use QoS on wireless. And this is a kind of very basic kind of thing. Everything I'm telling you is very, very high level here with Wi-Fi, by the way. So what we have here is a way of us being able to say, look, these are my most important packets. My voice packets and my real-time application packets are the ones that I really, really want to get through. So what I'm going to say is, rather than rolling a D20, you get to roll a D4. So you're now more likely to get a lower number. And I've given you the actual numbers here rather than the D&D dice numbers. And then what we can say is, look, this traffic, I really don't care about it. It's background traffic. Just get through when you can get through, but don't stress about it too much. And what's quite nice about when we start applying QoS onto wireless is that we also get these arbitration interframe spaces, which is this far number here. And what that says is, look, if I've got a voice packet and I've got a background packet that turn up at the same time, they both get to 0, what they also have to do is the voice packet gets to start talking really, really just slightly before the background packet does. So rather than have a collision, the background packet turns up, it's waiting its 7 arbitration interframe spaces before it talks, and it hears a voice packet and goes, right, I've got to back off, and I've got to double my dice and go again. And so that's why it's really, really important to use QoS. Why is that important nowadays? Is that what you'll find in your networks is everyone's using voice, everyone's using video. And so if we apply QoS, all we're doing actually is minimizing the amount of people that can be per AP. And so what I'm finding a lot of at the moment is I'm going into places and they're going, oh, wireless worked perfectly before, lockdown, and now we're doing hybrid working. We've got half the people here, but it's not working as well. Yeah, but that's because now everyone's on a Teams call, everyone's on a Zoom call, and actually that's the thing that's just causing problems. So again, that's how QoS works. That's why you might be seeing issues on devices and things. Right, my next kind of Wi-Fi 101. You've heard kind of buy cheap, buy twice. That doesn't work with Wi-Fi. In Wi-Fi, it's buy cheap, be miserable. So there's a cost of goods sold, right? Every vendor adds 50, 60 points on top of what it costs them to make the bit of kit. If you pick up a top-of-the-line Cisco AP, and you pick up a top-of-the-line Ubiquiti AP, one's going to weigh a lot more than the other. And it's not because they put lead in a Cisco AP, I promise. There's extra things like decent shielding, even down to the chips that are used, right? So you know how chips are manufactured on a wafer? And how all the ones in the middle of the wafer are really, really good chips. And then you kind of, towards the edge of the wafer, you get the binned chips. Guess which one's Ubiquiti buy? Right, the next thing that we need to realize about Wi-Fi is that every device is different. Not just every model of device. Not every iPhone is as sensitive to Wi-Fi as every other iPhone. not even every model of iPhone, the 13. Everything here is differently. So for instance, my laptop, my M1 MacBook Pro, original, OG, here's Wi-Fi about 10 dB louder than my iPhone 13 Pro. Now remember, 10 doesn't mean double, it means 10 times as much energy gets to my laptop than it does my phone. So when I'm designing Wi-Fi, what am I designing for? Am I designing for my phone or my laptop? Because those two networks are going to be very, very different. They're going to be designed very, very differently because one receives 10 times more energy than the other. So when you're going, oh, you know, all our phones work brilliantly, but our laptops, you know, are having real problems. Yeah, you have to pick one, unfortunately. You have to pick one. Devices do not shut up. And again, this is a great thing, right? So in a space like this, especially because of the density of APs, Hilton can track where we all are because our devices are they don't ever stop talking, right? So they're going, hi, I'm Dan's device. Are you my home network? No. Hi, I'm Dan's device. Are you Starbucks Wi-Fi? No. Hi, I'm Dan's, and every single network that I've ever joined, my device is probing, saying, hey, are you this network? Hey, are you this network? And we can actually use that in Wi-Fi to do things like track people and see where they are and where they move and where they're moving to and where they move through and all that kind of stuff. But also, the important thing to note is that because our devices never they don't ever shut up, and they're always talking, that's using up airtime. So if we've got a bunch of devices that are constantly, you know, remember, only one device ever can talk at a time per channel. If our devices are constantly probing and going, hey, are you this thing? That's using up airtime. And pretty much the only way of getting rid of that is to wipe the device. Okay, so we're on to channels. I'm very aware I'm like rushing through this. I've got so much to get through, and I'm aware that I've not got a lot of time. Channels. In the 2.4 gigahertz band, I hope everyone is aware of this. There are only 3 channels available. I know you get the option of 13. There are only 3 available that you should be using. 1, 6, and 11. If you're the person that goes, oh, channel 3 is free, I'll use that instead. You now make channel 1 and channel 6 not usable for anyone. Yeah, only use channel 1, 6, and 11. They are the only non-overlapping channels that we have in 2.4. And I'll come to why we only want to use those 3 when I talk about co-channel interference in a second. 5 gigahertz, this is where kind of most Wi-Fi lives, right, nowadays. So you can see here, we've got all these kind of different things. Uni 4 is proposed, it isn't here yet. Uni 3, we can use in the UK. Some vendors like to think that we can't. Not mentioning any. If you want to know, come and talk to me. And then the blue ones that you get here are the DFS channels, right? So DFS means dynamic frequency selection. Basically, Wi-Fi is a second-class citizen in those channels. So if a radar pulse goes off or something like that, we basically have to back off and say, all right, okay, we can't use that channel anymore and move to another one. So if you suddenly see 15 clients disconnect from your network, you've probably been hit by a DFS event. Doesn't mean we shouldn't use those channels. We should still use those channels. And there are some other things that you can't do in those channels. So things like clients can't probe. They can't ask, are you this network I should join? Until they've received a beacon from that AP. Okay? Which is another reason why we should never use hidden SSIDs. If you do that, have a word with yourself. We are getting 6 gigahertz. This is going to be a massive game changer. I know, like, every time there's a new wireless technology, it's like, oh, this is going to be amazing. This actually is going to be amazing. So this is where Wi-Fi 6 will actually work like Wi-Fi 6 is supposed to. This is where we might actually start seeing some OFDMA and more than one device being able to talk at the same time. And the reason for that is that we will have no legacy clients. There won't be any old clients that we have to still let talk, which we have to do at the moment in Wi-Fi. Unfortunately, Apple don't have any 6 gigahertz clients, so we'll leave that. Come on, Apple. Right, so we're getting to co-channel interference and adjacent channel interference. So it's known as co-channel interference. It's probably better to be thought of as co-channel contention. Basically, people trying to use the same channel. If you've got 2 APs, if you did a quick little Wi-Fi scan of this room, you'll see why I wouldn't have designed it like this. There are lots of APs that are using the same channels, which basically means they're one AP. Right? What you want to have is there are 23 APs in here. They could put every single AP on a separate channel, and therefore 23 devices could be talking at the same time. Now, because they've used 40 megahertz wide channels, it now means actually only half of those clients can talk at the same time. Okay? And that's why it's a poor design. What you want to have is like what I've got in this image here. This is from a company called MacADUK. And what you want to have are your APs on separate channels, but also not on channels that are kind of sharing shoulders with the channel next to it, if that makes sense. You don't want channel 36 next to an AP that's using channel 40, because it's a bit like when you're trying to talk to someone at the bar and you've got someone right next to your head and they're shouting at their friend. There's a lot of noise that happens as you're trying to have your conversation, which you don't want. So we want to separate those things out. What I'll do is I'll talk in a bit about kind of more in depth about where we want those cell edges to be. So how does a client roam? Well, the real answer is we don't know. Every client roams differently. Apple have kind of given us some information, and then we've kind of like gleaned other bits of information. But basically, an Android device will do a completely different thing. A Windows machine, depending on what NIC it's got, depending on what driver it's running, depending on what firmware it's, whatever, it will be different. iOS is a bit more helpful, macOS is a bit more helpful. So what we see here, we've got on the left-hand side, we've got the green circle AP, and on the right-hand side, we've got the purple triangle AP. It doesn't really show up very well on these screens. On my laptop screen, it's amazing. But basically, as we move from left to right, you can see our signal is coming down following that logarithmic scale, right? So we're moving along, and we've got free space path loss. The energy is getting lower and lower. But as you see, it kind of tapers out as you get to the middle. What happens is, on iOS, that roam trigger happens at neg 70. So when your device hits neg 70, it goes, oh, right, let's start looking for another device, another AP for me to join. But what it needs, if I'm using data, is an AP that's at least 10 dB higher than what I've currently got. So obviously, if I keep walking, you'll notice that that signal goes down, so I don't need 10 dB better than neg 70. I need 10 dB better than where I'm at. 8 dB, sorry. So you can see, basically here, this is a poor design for an iPhone. Poor design for an iPad. If we look at a macOS device, however, macOS will start scanning, start probing, once it gets to neg 75. But it always needs, whether it's using data or not, it always needs an AP that's 12 dB higher. And what you'll notice is, this here is a network that is designed for macOS. It doesn't work very well for the phone, but it does work well for the laptop. And I've got this at the moment where a company had, got their offices designed for the iPhone. They've since come back to the office since COVID, and they're now like, oh, we're trying to move our laptops from here to here, and it's still connected to that AP, halfway over the other side of the office. Yeah, because it was designed for an iPhone, not a macOS. So now we've got to go and redesign it so that it works for macOS. Does that make sense? Good, I'll take that as a yes. Okay, My next thing, don't rate limit Wi-Fi, ever, ever. Why? Go on, someone have a guess. Because only one device can ever talk at a time. So if I rate limit you're going to download your Netflix video, whether I let you do it quickly or slowly. And you're on the channel that all the rest of us are on. So if you're going slowly, we just have to wait behind you. Why would anyone ever rate limit Wi-Fi? Because they don't understand it. Don't ever rate limit Wi-Fi. All you will do is make everything else on your network go slow. Because remember, it's based on the channel, not the SSID, not the actual whatever, it's based on the channel. Marketing, that's why that feature exists. Right, so here we have it. Yeah, I've got 10 minutes. Whew. This is good, isn't it? Right, so iPad and iOS roaming, -70 trigger. So like I said, if it's actively using data, it needs to find an AP that's 8 dB higher. If it's just in your pocket, not doing anything, great, it will wait until 12 dB and then it will roam. So PMK caching is supported. Opportunity key caching isn't supported on iOS. KVNR, does anyone know what KVNR, okay, 802.11k, does anyone know? Good, this is the right crowd, I love it. So K is neighbor reports, neighbor reports. So that basically, if I join an AP, it says to me, just so you know, these are the 6 other APs and the channels they're on that me as an AP can hear loudest. So why is that useful? Because it means that when my device hits that -70 trigger, it doesn't go, oh, right, I'll start at channel 1. Are you the network I'm looking for? Channel 2. Are you the network I'm looking for? Channel 3. Are you the network? That will waste a lot of battery and a lot of time. What it will do is it will go, right, that neighbor report said to me it was channel 36, 106, 144, wouldn't be 144, 144, 149. I'll go and scan those channels first. Great, I found an AP on my first or second attempt that I can move to. Yeah? So you definitely want that enabled. 802.11v, there's a bunch of different stuff in there. If you've got a well-designed network, 802.11v is brilliant. If you have a really poor, what I like to call finger-in-the-air design network, you need to turn 802.11v off, because you'll have a nightmare. And I'll explain why in a bit. 802.11r is if there's lots of different things. The main thing is that if you're using an 802.1x network, rather than having to go back to the radius server every time, actually, the AP can go, yeah, that's fine, let him in. Really, really basic way of saying what 802.11r does. Okay, and then 802.11e, that basically says, the AP will say, look, I've got 40 clients connected to me, and another AP might say, I've only got 2. So 802.11v is useful because the iPhone will basically go, right, on that scan, okay, I've got this one, but that's got 30 clients attached to it. I've got this one, which is slightly lower RSSI, but it's only got 3 clients attached to it. I'll join that AP instead, because my airtime is going to be much better on that AP than it is on the AP that's next to me. Right, so now we get to this devices will gray or block list BSSIDs. If you have a poorly designed network and you use 802.11v, what happens is the AP will go, I'm too busy, here's a disassociation imminent packet. You're going to get a message that says, I'm about to kick you off the AP. If your Apple device gets that 5 times, it will say, I'm never connecting to you again. If it does it more, indeterminate, it will actually say, I'm never connecting to you, ever again. And that can be really bad for your network, especially if you have dual band SSIDs where you're presenting your SSID on 2.4 and 5 gigahertz, because now your iPhone will ever only connect to the 2.4 network, And as we all know, there's only 3 channels in 2.4 rather than the 24 channels that we have in 5 gigahertz. So it's much more congested. Right. Whew. Okay, this is all the macOS stuff. Take a photo of it. I'm not going to go through it all because I haven't got time. Apple Silicon now supports 802.11k VNR. That's the biggest thing you need to know. That's amazing. We've wanted that for a long time, and it basically now means that our macOS clients are going to be much, much better on wireless, especially as we move into this age of people picking up their laptop and moving somewhere else. That's really important. Okay. These are my kind of best practice tips right at the top. Right, we design for neg 67 at the cell edge. What do I mean by that? What I mean is, if I'm stood away from an AP, if I get to neg 67, I want to turn around and there be another neg 67 AP ready for me to go to. Why would I pick neg 67? Anyone? Correct, because the iOS trigger is neg 70. And remember, that's double the power. Right? So we want to have it so that I don't hit the cell edge and all of a sudden I've got nowhere to go and then my phone has got a bad experience. Always use single band SSIDs, do not use dual band. If you've got a 5 gigahertz capable device, you want it using 5 gigahertz. You do not want it using 2.4. So create a separate 2.4 SSID that's called IoT or legacy or slow or don't use this, it's rubbish. And just make sure that your 5 gigahertz capable clients are on 5 gigahertz. So the max power that an iPhone can send out is 17 dB. So what you want to have is an AP that's not really, really loud and devices that are much quieter, because as you walk further away from the AP, it's then going to, the AP might struggle to hear it back. There's a kind of bit of a debate about that, but for me, it's just best practice. Does anyone know what RRM is? Correct, radio resource management. So that is where your APs will turn themselves up or down, and they'll change channel and things like that. You want to try and restrict that as much. If you've got a good design, try and restrict that as much as you can. Because what you don't want to have is an event space like this, where it's hardly ever used, and all the APs start turning themselves up really loud so that they can start hearing clients, and then loads of people come in, and now your experience is really poor. Always use 802.11k, no excuse not to. Use 802.11v if you've got a well-designed network. If you go back and you find that your network is using 802.11v and you haven't had a design done, turn it off. Don't ever hide an SSID. Lots of reasons why. If you want to know, come and ask me. It's not a security thing. Do not use channel 144 in the UK. I sell a lot of Cisco. I install a lot of Cisco Meraki kit. Out of the box, it comes enabled with channel 144. No Apple device in the UK will use channel 144. So make sure that's turned off. And reduce your number of SSIDs to 3. I can show you a graph, a chart, about why. Trust me, you want to make sure that you have as few SSIDs as you possibly can. Right. Okay. This is a quick little video. So this is a bit of software called Ekhow. This is what I design networks in. It's also kind of what I do surveys and things in. What I want to do is show you Apple Wireless Direct Link. Does anyone know what Apple Wireless Direct Link is? There's a clue. Green. AirDrop. Yes, well done. Right, AirPlay, AirDrop, the iPhone transfer thing that you do, all that kind of stuff, all uses this proprietary Wi-Fi technology called Apple Wireless Direct Link. What I want to do is show you how this affects us in the UK. So in the US, Apple Wireless Direct Link uses Uni 3, which is channel 144 and up. And that's really useful because not a lot of things use that. In the UK, though, Apple went, fuck it, just put it down in Uni 1. And so what we have is actually Apple using channel 44 rather than 36, but at 80 megahertz wide, which is these first 4 channels right to the far left. So you can see there that blue, dark blue box that I've got over that far side is actually my neighbor's AP. So what I wanted to do is demonstrate to you how Apple Wireless Direct Link can ruin your network. So this video, so the middle one there is my normal network. On the left, I've now started a transfer, an AirDrop transfer from my phone to my laptop. What you'll see is that box will disappear. That is my neighbor's wireless network disappearing for a bit. There you go. He no longer has a Wi-Fi network. It does come back. I'm not that mean. There you go. So you do need to be just wary of, if you've got like, I've done a lot of design studios and things like that, where they're constantly airdropping files to each other, and then they were like, oh yeah, our wireless just dies every time we're trying to do things. Well, that's why. So just be aware of it. Right, these are the tools that I use. There's a whole bunch of stuff there. I do want to show you one really quickly, which is a tool called N-Oversight, which is by a British guy called Ben Toner. He's actually giving 15% off to anyone who's here if you use MacAdUK on his software. I think it's about £100 a year for a license. It is the best money you will ever spend, and I will show you why. So on the right-hand side is the N-Oversight software. What that's doing is it's actually pulling the logs off of my iPhone and then displaying it so that I can see exactly what's happening. So I can see my RSSI, my SNR, I can see which APs I'm moving to, I can see why the phone's decided to roam, how it's decided where it's moving to, all that kind of stuff. Top left is a bit of software called Wi-Fi Signal by a guy called Adrian Granados over in the US. That is showing you macOS. So you can see my Mac is connected to an AP on channel 100, and my iPhone is connected to an AP on channel 128. Those devices, even though I'm stood in the exact same place, have chosen separate APs to use. Okay? And then this is just a WebEx call so that you can see how great the Wi-Fi is. Yep. And then what you can see here is every time that a session goes into the red, that is where basically I'm dropping below that neg 70 trigger for the phone. As soon as it hits neg 70, it should move straight away to a new AP. So if you ever see like an amber or a red, you basically know that the Wi-Fi, the roaming for an iPhone isn't working properly. Great, so I want to show you that because it's an awesome tool. It's amazing for checking how iPhones and iPads and stuff work. Another great tool which is free is the Apple Wi-Fi profile. You used to only have to download this every 30 days. It's now 7. Cheers, Apple. But it does now come with their new responsiveness test, which is lovely. And basically, this is a profile you can download from the Apple developer website. If you go to that URL, I've actually created a Siri shortcut that will do all the finding the profile for you and just download it. So only do that if you trust me. I'm trustworthy, I promise. Other things to consider, I'm a bit behind now, so those things. Cisco do have a technical partnership with Apple. So there are things that you can do with a Cisco network that you cannot do with any other network provider, any other vendor, when it comes to Apple. Apple use Cisco. Okay, one more thing from me. Captive portals, don't do them. Oh. You don't charge people to use the escalator rather than the stairs. You don't make people sign an acceptable usage policy to use the escalator rather than the stairs. There is no legal requirement in the UK for an acceptable usage policy. There is no legal requirement for you to ever use a captive. There's probably people that sell captive portals. Don't ever use a captive portal, right? No need. Fast, free, frictionless Wi-Fi for everyone, and your users will love you, okay? That's me. If you want to know more about me or Natilik, this will take you to a contact us page. Even if you don't fill in the form, do you want to just scan the thing so that Natilik go, Dan got loads of interaction at that event. We should definitely send him again next year. That would be great if you could scan that, because they're counting every single scan that gets done. So that's me. Thank you very much. Are we doing questions? Go on then, questions. They're not, but they can be. Yeah. Absolutely. The slides will be available. Yeah, if anyone wants to. Please come and talk to me. I'm new here. This is my first event, so do come and ask questions.
Hey, Robin here.
Hi.
Is this on?
It is.
Good. So you say you can design a network for iPhones or for Macs?
Yep.
Is it feasible to design a network for iPhones and Macs?
If you're very skilled, it is, yes. No, it is feasible. It is difficult. And I think just knowing those different things like the trigger thresholds and things like that, you can basically try and find a balance between the two. So, yeah, there's always going to be some compromise. What you're trying to do is optimize it for the best thing. So what I tend to say is the least capable but most important device. Sometimes that's the CEO's iPhone, right? Sometimes that's the barcode scanner in the warehouse, because actually if that doesn't work, the whole business doesn't work, you know. So you always design for the least capable, most important device. Oh, go on. Oh.
Hello. First off, that was brilliant, so helpful. Thank you. A couple of quick questions. This is maybe quite a basic one, but in terms of enforcing 5 gigahertz versus 2.4,
yep.
Is that something that you would do at the client end via MDM or at the AP end?
Yeah, no, so I would do it on the AP. So I would effectively say this SSID, the SSID that gets broadcast is only broadcast on the 5 gigahertz spectrum. So it's just not available to people on the 2.4. That's the easiest way to do it.
Right, and a very quick thing, it might not matter. I know for things like sound and audio, dB scale would be dBA. In terms of the radio Wi-Fi, what would that be in terms of decibels, or does it just not matter for this context?
Yeah, so every AP and therefore antenna has got different gain. So you can set a power on a controller to be, say, 14 dB. Some antennas have got positive gain, some have got negative gain, so that will adjust what comes off. But bear in mind, it's coming from that free space path loss thing, right? So it starts at the antenna at, say, 14 dB, but by the time it gets to here, it's at negative 40. So we're talking, what, 4,000 times less power by the time it gets to here, yeah.
Cool. Thank you very much.
No worries. There was another question, yeah.
Hey, so I think you mentioned RRM in terms of dB and limiting the range.
Yep.
The Meraki kit offers smart channel switching.
Yes.
Would you encourage using that or not really?
If you don't have a well-designed network, yes. If you have a well-designed network, then what you would tend to do is have AP redundancy built in. So if a particular AP had to shut down off that channel because it got a DFS event, there should be at least one other AP that's at neg 67 that could take those clients on, and so therefore you wouldn't have a coverage hole. Again, one of the things that we used to do with Wi-Fi was design for coverage, right? So we would put in 3 APs and turn them up to 11 and go, job done. Whereas now we have to design for capacity. And so nowadays, when we're looking at people that, everyone's just got a Zoom call or a WebEx Teams call happening all the time on their desk while they're doing what they would normally have done, all of a sudden, we can now have 12 people per AP rather than 50. And so, yeah. Great. So, yeah, I would tend to design static channels on a proper design. Yeah. Some people would be like, nah, just let the computer do it. Well, I don't trust it. Great. Thank you very much.